I'm Toppin. I am the VP of Engineering for Infobright. I'm going to talk today a little bit about high-performance near real-time analytics. I mean, it's a long sentence. Marketing created that. What I'm actually going to take you guys through is a few different ideas that we've had about how you can build large-scale analytics applications using MySQL, MapReduce, actually key value stores, and Columnar database. Now, for a lot of these, I will be using Infobright as the example, but the truth of the matter is, under the covers, a couple of these solutions have been able to leverage many different hybrid stores, right? So, a lot of times where you see the Columnar store, you could put in Infobright, VectorWise, Vertica, whatever else. All right. So, what we'll talk about today, a couple of things. We'll talk about the general motivations for designing these types of systems. And we'll go through a quick overview of, first of all, the domain in which these systems are relevant. Why would I care about, processing several terabytes of data, and why would I actually care about having consistent loads? Why would I care about having sub-second and consistent response times as I scale the system? We'll talk about what near real-time analytics mean, and we may also touch, I'm not really sure yet, we'll get to that in a second, but we may touch a little bit on what exactly the differentiators are for columnar databases and how they relate to NoSQL and other pieces of technology. Then we'll go into the meat of the talk, and we'll have to go pretty quick here, but we'll go into a few live examples. So I'm going to walk you guys through a deployment that we did in China with Nokia Siemens Network, and then I'll walk you through a reference architecture that we've done for some very large customers who I'm not going to talk about specifically. So first off, a couple of quick questions before I get into this. How many people here are familiar with Columnar Stores? Yeah? Okay, good. So we're going to breeze through the Columnar Store description part of this. And if anybody has any questions afterwards, come and talk to me. I'll be happy to go through them. Okay, so what you see here is incredibly simplistic, but this motivates almost all of our application design. For us, how long it takes to process this cycle, to actually get through from data to information to decision to action, and how tight that is, the cycle time that we realize is key to many of the applications that we're talking to. And in particular for Infobright, we actually focus very much on the time. How long it takes for you to set up your system, how long it takes for you to maintain the system, how long it takes for you to get the right result, and how long it takes for you to get action based on that system, right? The reason that this is so important is because obviously the size of data is growing. That sounds trivial, but for us, in the small to medium-sized business market that we target, we've seen in the last year deployments go from a typical size of 1 to 10 terabytes up to 10 to 100 terabytes, and we expect to be handling in that same sector well beyond that within the next year or two. And this is very important because as your data grows, if you want to keep your total cost of ownership down, as you want to keep the manageability of the system down, you have to start thinking about data in very different ways. So you can't go in thinking, for instance, that the same sort of exact query mechanisms that you use will still apply. You can't go in thinking that standard load paradigms will apply as well. So how much time we spend resolving questions and answers and vice versa really decides the success of all of these systems. Good example is if you're analyzing event data for, say, mobile analytics. So to use an unfortunate incident, I don't know if you guys remember last year when that senator got shot. So it's a terrible event, but what was interesting there is that we had a couple of different customers with a few deployments that look similar to what we have here who were monitoring the event. Part of their business was actually to monitor and process the event and then have reactions to it. What was interesting there is that the typical MapReduce type approach just by itself didn't give the proper response time. So a huge competitive advantage that people were able to achieve was in the hybrid approach. So people who had a MapReduce tied to a Columnar store for quick analytical processing, plus a complex event processing front end to manage the events. So the market that we really target in the SMB, and this is a key distinction, because as you'll see, the systems that that we're going to discuss have, I would say, much looser transactional requirements, different characteristics in terms of the types of queries that can run and so forth. It's really tied to what we call the machine-generated data problem. This was a term that was coined by Kurt Monash last year, and it's actually turned out to very well characterize what we do. So for us, machine-generated data is anything to do with weblogs, mobile advertising, network events, call data records, financial trades, anything that is high volume, generated from machines, or tracking what humans are doing would be what we would call machine-generated data. Okay? So when it comes to the near real-time analytics, for us, we want fast, scalable, low-latency loads and queries, but the loads are very important. The reason for that being, of course, that if you look at telco applications, as an example, if you go into any of the large providers, you're talking about aggregate across the network, several terabytes in an hour. So probably we're talking 400 or 500 terabyte loads per hour. You're talking spikes well above that, and data retention rates which are much higher. So it isn't just a corner case. If you're looking at storing, say, a week of data, you're looking at aggregate about 4 to 10 petabytes of data, right? And that's where the support for line rate data comes in. So backbone, trading information, all of these have the same kind of characteristics. And part of what we look for here is also consistent response time. So as the data grows, the load has to maintain somehow. As you heard Baron mention in the previous talk, for those of you who were here, it's, there's no such thing as pure linear scalability, but it has to be well characterized, and you have to be able to scale the load with the size of data to a point and actually have mappings beyond that to tell people, here's how you're going to grow with the system. All right. The last, probably the trickiest part of all of this is that when we look at running aggregate queries, so where we're looking for characteristics, trend analysis, churn analysis on a system, where we're looking to go through that whole data lifecycle that I mentioned before. You're recognizing an event in the system, recognizing a trend, and then from the trend you want to be able to drill down to particular events and then come back up again and drill back down again. That whole sort of telescoping up and down through the query. That's exactly the type of query model that we have to be able to support in these types of systems. All right. So I'm going to start skipping through these slides because I think we've, enough of you know about Columnar Stores. So this is self-evident, as we've said before. Columnar versus row databases, you guys know already about the storage on disk. The cases where row-oriented versus columnar works. Probably the most important thing here is that for us, in these types of cases, where we look for table scans and generating events, we go to a large MapReduce type store. When we get into the analytics or particular event analysis, that's the Columnar store. Okay, and we're going to skip through this. Can you guys read this? No? Okay, so I'll just talk quickly through it, and this will be in the slides that are put up on the page afterwards. You guys can take a look at it. What this is a comparison between row columnar, NoSQL key value store, NoSQL document store, and NoSQL columnar store databases, because each of them have different characteristics. When we mix and match our architectures, we actually use these characteristics to create a final solution. Right? So a good way of imagining it is that take the obvious scenario. A role-based we use for any transaction management up front. Anything that's going to be particularly high rate requiring strong transactional support. Columnar we use for any analytical store. The NoSQL key value store is point-in-time event analysis. The document stores when you're actually getting retrieval for audit and other purposes like this. And NoSQL columnar store is where we're doing huge batch type table scan analysis where the response time isn't necessarily important. We can wait for it. Okay. Any questions, by the way, so far? All right. Okay. So with all that aside, let me talk a little bit about a deployment that we recently completed with a partner, Brainchild, with Nokia Siemens Network out of China. And in this particular solution, we used Hadoop, MySQL, Infobright, and Pentaho. And so the problem was they had 2.6 terabytes per day of network traffic. The bulk of the data was being thrown away. And when they tried to run reports on it in a standard store, and they were using a MapReduce store to begin with, the report performance took forever. So in other words, the amount of time for which that network data was useful was actually becoming lost because they weren't able to run the reports. It's a classic story. We had no historical data storage, and they needed a quick reporting engine. So everything was stored inside of Hadoop. They used Hive to massage and create an ETL process to then feed a reporting repository, which was Infobright, and all of the analytic front end was Pentaho. So the way they did this was they actually had the load jobs coming in. They used JSON data to load into each of the nodes. So that was where they were doing their splits and aggregates. And then they built a single set of files, which was their reference data. Now, the key thing here, as we'll see, as opposed to our later analysis, is that this was not what I would call a complete real-time analytics system. By that I mean, yes, there was consistent response time, but the window between the data being available and when it was actually brought into the system was wider than I would actually call near real-time. Okay? From here we had an ETL process that brought it into Infobright, and then they had analytics on this. So everything was retained inside of that 4 petabyte storage. They did the cleansing, aggregation, and load into Infobright, and we had a 100 gig to 100 terabyte 100 gig to 10 terabyte, which translated, I'm not sure what their compression ratios are, but let's guess that it was up to 50 terabytes, which was summarized inside of Infobright and MySQL. And then they ran Pentaho against that classic solution. And this gave them their reporting analytics. Okay, so what was interesting about this was that from here they took a look at what the performance characteristics were of each of the different types of system. So you can see here the performance for the Hive Hadoop solution actually per node was actually increasing. That's a little bit more than the Infobright nodes, and the Oracle MySQL clearly was not able to scale by itself up to the size that they wanted. In addition, they had these the hardware costs start to show at this point as well. So the single Columnar store for a much lower price point was able to give them the same performance as the transactional store. Just another example of where your choice of tool is extremely important. So the results from all of this were that they were able to get their running 90 days of data. They're able to store everything, and it was all done using open source technology. Scalability was not unlimited, but it was good enough. Any questions on this? All right. So let's move on and talk a little bit about what I would say is our reference architecture. Having looked at this last architecture, and actually even from before, seeing architectures like this, we wanted to change a couple of things. Probably the most important thing we wanted to do was change the data availability time. So we wanted to make sure that as the load was coming in, the data was actually freshly available. As you'll see, what we did was we took a MySQL Infobright, and we actually rethought our load. So the requirements that we had out of the box, we separated the architecture into query nodes and load nodes. Roughly 5 to 10 load nodes per query node. For each query node, we had 1,000 to 10,000 users per node. The requirements were pretty hard in terms of the simple queries. So for our point-in-time analytical queries, we're looking at less than 10 seconds for the simple queries, and less than 10 minutes for complex aggregates across all the system. Greater than 10 terabytes per hour per database node. So each of those query nodes was holding in excess of 10 terabytes. It was dependent on the class of system that we were looking at, but some of them had upwards of 50 terabytes per node. And the loads were between 100 to 500 megabytes per second. We needed low I/O latency because the same load nodes that were actually bringing in the data were the same nodes that were bringing in, were actually reading and parsing the packet data off of the line. Hundreds to thousands of nodes being used. So we wanted to have all of the query and load nodes distributed over a wide area, so there's no fixed data center. Low maintenance, as simple as possible. We wanted the query times to be stable, and probably the most important thing here is that the transactions actually weren't needed because we were able to create a sharding architecture where only a few of the nodes were redundant throughout the entire system. The biggest problem that we found was actually not the queries for a few different reasons. One was that we were able to pre-calculate most of the queries. But then the other thing, from the ad hoc point of view, there were only a few interesting dimensions that we could find in the data, and those were sharded out ahead of time. And those were loaded into the Columnar store. Probably the biggest challenge that we had was that we found that in terms of the loading rate, it wasn't easy to distribute, and it wasn't easy to have the availability done immediately. So what we did was that we actually broke apart the load so that all of the intelligence associated with the load was held in a single logical unit. That meant, just coincidentally, that there were no particular indexes, that all metadata and everything else that was required for a particular load needed to be calculated upfront on a single load node independent of the query node. So completely disconnected load processing. The data would come in from a set of workers. There would be an aggregator off of whatever the line data was, whether it was telco, financial data, or otherwise. All the parse, calculation, and compression of the data was done solely on the load node, and each of these was independent of the other. Now, the real benefit of this, because we were compressing the data up front, was that when it came to actually loading things into the query nodes, our transaction model changed significantly in that now all of the loads were basically copies of compressed data. So in one end, we had 500 megabytes coming in per second. And out of the other end, in terms of the compression, we had anywhere from 10 to 50 megabytes coming. So we lowered the network latency that way. And then when it got to the database server, we changed the transaction model so that we were just copying or appending to the database files as they came in. In most cases, the copy was less expensive than the lock acquisition under high load. So to a single table, using a simple read commit model, we were able to achieve fairly high throughput, right? Just by setting up each of these load nodes and what we call data processors to remotely calculate and compress the data and load it, we were able to achieve these high throughput rates very quickly. Okay, so how everything ended up looking in the end was something like this. So, no microphone that can move with me. So here are each of the network sources. These are the load nodes here. We would separate each of the load nodes at ETL. So there's an ETL tool here, and we'd create user data. So all of the phone numbers, log data, web identifiers, cookies, things like this were created into a user dimension. All line rate data was created here, and packet data, fact data was loaded separately for ad hoc analysis. We also created off of these a key value store just for quick lookup, so that all of our existential queries were fast. The interesting thing here is that in some deployments, people actually use a simple MyISAM database per query node. So this ended up being probably about anywhere from 10 to 100 million records, very simple records which perform well in MyISAM. For larger deployments, they use things like MongoDB. And from here, the other complex part here was that we had a query generator which recognized all of the shards, created all of the reports from up here. Ad hoc analysis would go to the Columnar database, and all of the other batch reports would come from here. Yeah, and this was basically the entire reference architecture for the system. All right. So, any questions on this? Yep. There was, but somehow it wasn't as important. So in this system, we can't drop data. In this one here, in the previous one, it wasn't so critical because there was replay in terms of all of the split files that were had. So there was a simple interface to replay and re-import the data. It was different here because we couldn't drop anything in these ones in most cases. All right. So yeah, the loss of load data over here, not well. The way that we handled it over here was that we actually loaded to several different nodes at once initially, and then had basically a phase commit afterwards. It wasn't a complete two-phase commit, but we actually were able to retain data there, right, using that. Good question. Any other questions? No? All right, I think I'm done, guys. Thank you very much.